I forget what the topic was, but you were going to do something.
I can do something just about any time. I actually have the slides. I put them together last week sometime when I was.
What was the topic again?
Inline Perl packages.
Right.
And other code snippets.
Inline Perl packages?
Yeah.
Perl minus capital M?
No, not that kind of inline. It's just the sort of thing that you don't put into a .pm file. You put it into a script and you customize it for the script.
Oh, sweet, yes. I was just wondering about that a few weeks ago.
That's handy if you just want to override one method and you can
Mm-hmm.
Well, the stuff I'm going to show is some specific tools. But,
Dave,
yeah.
can you also send me a description that I can put up on the
You
website?
bet.
Yeah. All right.
Then you'll invite people to it, and we'll have
Yeah.
meetups.
So how's the German chocolate cake there, Dave?
All right. So given that, I believe we are ready for the Perl Encryption primer. If anybody, I don't know if you guys have been following, Tim has actually been posting little snippets of this to his blog and also out on blogs.perl for the last month. So that's been a very interesting read. So if after the talk, we'll also put the slides up on the site, but if after the talk you want more info, I definitely encourage you to check out wumpus-cave.net. That's his blog. It has all kinds of cool posts about this very topic. So without further ado, Tim, take it away.
So, Perl Encryption Primer. What I'm hoping for this presentation is not just going through the Perl code and showing you how to put together a lot of encryption, but also going into a little bit more of the whys of what each one of these things are. So starting with random numbers, which is the building block of any kind of encryption. If you do not have good random numbers, nothing else here will matter. Then one-time pads and why you should not use them. Block ciphers are a form of symmetric encryption, meaning both sides use the same key. And now that we have public key crypto, it seems like that should be kind of obsolete. But it turns out block ciphers are still very useful. Then hashes, how we take one big document and generate some kind of ID that will identify that particular document and no other out there, we hope. And then finally, how we kind of tie all this together into storing passwords, which is something a lot of us are going to deal with in any kind of web application. We have to figure out how to do this. So the trouble with random numbers is computers are very, very deterministic machines. And that makes randomness very, very hard. And the first big thing that you need to know is to never use the rand function. This is just part of the standard C library, and of course it's in Perl as well, along with most of the standard C library. And we'll show an example of why that's so problematic in a bit. But there's many different CPAN modules that will give you a good random number that will work across different platforms. Crypt Random, as good as any. You can find a few other different ones out there. They pretty much all either hook into Linux has /dev/random, which is a good source. And if you're not on Linux, if you're on Windows, you have the entropy gathering daemon, which works basically the same way the Linux system does for dev random. Macs, there's all equivalents. BSDs, there's all equivalents. Encrypt Random will just link into whichever one is appropriate for your system. What would be even better if we all had hardware random number generators. Something like that's based on the decay of a radioactive element, which is quantum decay, so therefore it's truly random. And there's other sources as well that you can use. But a hardware random number generator would be great, but they're either really cheap and then you wonder if they're good enough, or they're really expensive and you still wonder if they're good enough. And since everything else depends on the random number generator, this is really important to get right. So here's what happens with rand, and I've got to get my pointer out here. Give me one moment. So we see in this little snippet, we are seeding the random number generator, which is 1, 2, 3, 4. And then we're calling rand 4 times. Then we're going to reseed it with exactly the same number. And again, calling rand 4 times. And we see in the output here, it's giving the same output both times. So if you were to, say, generate a 128-bit key for a block cipher, if you stuck in a number into SRAM here, you don't have to brute force the 128-bit block cipher. You just brute force this input, and then you generate exactly the same output the next time. This is only about 32 bits, depending on your platform, I think. 64 bits on modern ones, I'm not actually sure on that, but 32 bits, 64 bits, that's pretty easy to brute force compared to a more modern block cipher. And there's other things as well within RAND that it kind of cycles through. It'll start repeating itself a little too soon compared to a better one. And bottom line is RAND is only good for games, and then even only simple games. Some of the professional poker sites actually have people that are experts in generating random numbers to run all their cards. So it's really for simple games, very simple uses, not for encryption or anything serious.
So if you don't seed it, does it get seeded automatically?
Yes, Perl does have a fairly sophisticated way of seeding. It's something more than just the recent timestamp, which is what you'd probably find on a lot of, if you were using the basic C library, I think that's what would happen. But Perl has a pretty sophisticated way of seeding that if you don't already, but it still don't use it for anything important. So this is crypt random, and so it just exports this make random function. And the size here is in bits. Strength says that you want to use Linux dev random or whatever the equivalent is on your system. If you say strength equals 0 here, it will use dev urandom, which is okay. Dev random will take data from keystrokes, hard drive timing, things like that. And on a headless server, a lot of those inputs will dry up very quickly. And so dev random will just sit there until it's satisfied that it has enough data to give you a little more. Dev urandom will keep spitting out, but then is it really strong enough anymore? There's some debate about whether that's good enough or not. If you're a little paranoid, go ahead and put this strength parameter there.
So strength of 1 is better than strength of 0, is that?
Yeah, it's just a flag.
So, right, and it just determines,
It's
you
the,
said urandom or random.
yeah,
The 1 is better than 0, you said?
okay, one-time pads are very, very simple type of encryption. And I'm going to explain this and then forget all about it except for winning arguments on the internet. This tends to come up every once in a while where somebody hears about it and thinks, this is the Jesus cipher that's going to save us all, and it can never be broken. And it turns out there's some very practical reasons why we never use it. But just as a building block, we have the exclusive OR operation. So here we take the ASCII value of capital A, which is 65. Then we're going to XOR that with 10. And we get 75 out of that. If we XOR that data with 10, we get the original value. And whatever value you XOR that with, it's always going to end up with the original value this way. You can work through the truth table and figure all that out. For now, just trust me, this works.
So that's all they do with one-time pads?
That's the idea. It's you have just a big long string of bits that's just the same size as whatever you're trying to encrypt. So you could also do this with subtraction and addition, but XOR is nice because it's
simple.
It's this reversible operation here. So this is how you could do this with encryption. I just use this crypt OTP module, which just does this XOR operation internally. So in this case, we have 8 bits times 25, because we've got a 25 character string down here, and we're just assuming ASCII, so it all works. And then encoding the output into base 64 so we don't mess up our terminal output. And so we just take the random number we generated up here, run it through OTP, and my grandma makes good pie. The one here just says that it's going to run off this string rather than using this as a file name. And then we get our output, and then we could decrypt this just by undoing the base 64 and then XORing it with exactly this same number. Now the great thing about this is that, technically speaking, if you do everything right, this is completely unbreakable. And the reason for that is that all messages of the same length are equally likely. There is some other key out there that would decrypt to any of these messages. And you can see here, we don't need, if we can just take out spaces, then we can get an even longer message in, and you just hope the person on the other end figures it out. Or on this one, we have a little bit of padding, so all the attacker can know is that it's at least that long, but it could be technically shorter. So the attacker can't even assume a certain length. They're practically unusable, though. The pad has to be the same size as the plaintext. And if Alice and Bob want to communicate with each other, Alice gives Bob this big key and then gives him this message. Well, why did she need to give him the message? Why couldn't, or the key? Why not just hand the message over to him if they had a secure way of doing this already? Also, you cannot reuse the key ever. If you do, it's very easy for an attacker to break it.
Hence the name one time.
One time. One
And
time only.
basically, when you meet, you have to transfer huge amounts of random data. And then you can do all kinds of things with what you've got, but
Exactly.
once it's spent, it's spent.
Yeah. So the other thing is, have to completely destroy the key afterwards. If an attacker named Mallory, what we usually call attackers in cryptography is Mallory. If Mallory goes through your garbage and sees, oh, here's a big piece of paper full of random numbers. Well, now he can break it quite easily. So you have to be careful about that. And what it comes down to is OTPs are almost never used outside of very, very high, top secret diplomatic communications. And governments will have all sorts of policies about, they transfer the key with this guy who's handcuffed to a briefcase. He doesn't even have the key on him. That's already at the embassy. He gets there, and then there's this whole ritual of how it's taken out of the briefcase and stored away, and another ritual for how this gets used eventually and then burnt later. And it's all very complicated and only worth doing if you want to be incredibly sure this will never be broken. So this completely fails the human problem, which we find out the math problem of cryptography is kind of done. It was not easy to get up to there, and there might be still some work to do, but it's kind of done, and we've solved it. The human problem is a much bigger thing. Keeping people from writing down their passwords on a post-it note and sticking that on their monitor, that's a real problem. That's the hard one to solve. And so OTPs are very big failures on that human problem. That's why we never use them. Block ciphers, though, we use all the time. So they're called block ciphers because they work on a fixed length of the string at once. So usually 32 bits these days. The old standard was called DES, and it had a 56-bit key length. And the great thing about DES was that nobody really figured out a better way than brute force to break it. There wasn't a great deal of improvement there. The trick was that at 56 bits, by the late 90s, it was perfectly feasible to brute force it. And so around this time, people started looking for something better. It should be noted here, if you have an n-bit cipher, it's 2 to the n security, so it's exponential. It's not a 112-bit block cipher is not double the security of a 56-bit block cipher. It's exponentially more. Going to 56 to 57 bits is doubling it. So the first attempt to improve on DES was, let's run DES 3 times using 2 different keys. So that's a 112-bit key. And that's very awkward and slow, and people didn't like it very much, but it did work. And so NIST, which is a big United States government standardization committee for technical things, they started a big contest, and a bunch of cryptographers submitted entries. And eventually they chose one called Randall, and that's now called AES. If you look around on CPAN, you will generally find them under the Randall name, not AES. I've noticed just when I started this presentation that there's a lot more out there under AES now, but under the crypt namespace you'll find it as Randall for the most part. And this goes from 128 to 256-bit keys. And you might ask, when are we going to be able to brute force a 256-bit key? Okay, well, there's a thermodynamic limit on how much energy it takes to flip a bit in an ideal computer. And that's this very, very tiny number here. So if we assume that we can't improve on a brute force attack, so it's clear if we brute force it, we're flipping all the bits through the keys in sequence and then trying to decrypt with that key. So the sun puts out this much energy per year, and if we could take all of that, convert it 100%, perfectly ideal energy conversion, put that in our perfectly ideal computer, and run it for a year, we could flip through 187 bits. That's not even doing anything with those, that's just counting. And if we then converted a big supernova blast, we could get up to 219 bits. So we're still not up to 256 bits, and we're still not even doing anything, we're just counting. And therefore we think that a 256-bit block cipher is probably as secure as we're ever going to need it.
Even though there are people making 1028s.
Well,
Or
that's
1024s.
That's mainly for RSA, which is a little different.
Oh, okay.
So, this comes right off the synopsis for the Crypt Randall module. And you'll notice when you look at it, it has this weird mode CBC thing. And this set IV. What's supposed to go in there? You just wanted to encrypt it, and you've got to deal with this nonsense. And there's actually a very good reason for that. But before we go on to CBC mode, we'll back up a bit and explain ECB mode. ECB mode means electronic cookbook. And this comes up because, in theory, if you could take your key, you could generate this giant cookbook that every plaintext block is mapped to a ciphertext block for your given key. So instead of having math happen in between, you have just this big lookup table, and you could do it that way, and it'd all be very fast. There's a problem with this, though. Let's say we had a bank account transaction message. So we have a 32-bit source account, 32-bit destination account, and then a 64-bit amount. So we've got this little structured message here. Mallory's been watching the bank's data go over the wire, and he notices every time Alice and Bob send each other money, the source and destination numbers are the same. They're encrypted, but they're exactly the same because they're in cookbook mode. It always maps exactly the same. That means he could put in a transaction of his own, get his encrypted account number out of it. Then when he sees Alice and Bob send each other money, he rips out the destination account and puts his own in. He didn't have to decrypt anything. He just had to know there was some underlying structure to the data. And if you think about any kind of message you can send, there's almost always some kind of structure to it. There's HTML is always going to have tags. JSON's always going to have bracketed data. You can't really assume there's no structure to your data, and so this sort of attack Mallory might have to get clever, but he can probably find a way. So the way we fix this is with cipher block chaining mode. So this time, we're going to encrypt the plaintext block just like we did before, but then we're going to XOR it with the previous block. And then since the first block had nowhere to go with that, there's this entitalization vector. So that's if you got through...
Initialization.
Initialization. Yeah. Okay, I didn't spell check well. But anyways, so since that first block didn't have anywhere to go, it has to have the entitalization vector, which will be the same size as the block cipher is, so 32 bits usually. And that should again come out of a cryptographically secure random number generator. And now when Mallory does this little trick where he's reading down the wire, he knows there's different numbers every single time. So he can no longer do this little trick, as long as he can't predict the entitalization vector. There are a few issues with CBC mode, not really in terms of security, but in terms of practical. If you wanted to do random access, like encrypting your whole hard drive, if you asked for a file in the middle of your hard drive, it would have to start at the entitalization vector and work all the way forward. That doesn't really work. If there's an error in an early block, in the bit, that's going to propagate to all blocks after that. And all these newfangled multi-core CPUs we've got, we can't parallelize them across that because each block depends on the one before it. So there's a number of different, more exotic modes that I won't really get into, but if you need to solve any of these problems, use counter mode. We won't really get into that either, but that's probably what you want to look at. So public key crypto. This is when you have a public and private key. And there's many different types, but we're going to focus on RSA. And RSA is based on the fact that you can generate two really, really big prime numbers. Relatively speaking, that's an easy process. It's easy to multiply those two big prime numbers together. But if I just gave you a big number and said this is the product of two primes, figure out what the original primes were, that's very, very difficult. People have been trying to figure that one out for centuries, and it doesn't look like we're going to solve it anytime soon. And quite possibly it can't be solved, although we don't know that for sure. RSA also gives you a little bit more than just encryption. So Alice will take Bob's public key, and she can encrypt a message to Bob using that public key. Bob is the only one who can decrypt that message with his private key. Bob can also sign the message with his private key, and the way that works is he just encrypts the message with it. And that means the RSA is kind of reversible this way as well, that you can decrypt the message with the public key. But the only way you could have originally done that is if you held the private key, so therefore Bob was the only one that could have done that. And also you can do both together. If you both have each other's public and private keys, you can sign and encrypt a single message. So again, there's a couple of different modules you can use to do this. I just chose GNU PG for the examples here. I think there's also Crypt Open PGP is another one. The GNU PG module relies directly on the GPG command line program. GPG is an implementation of Open PGP, and PGP is the original one that brought all this to the forefront in the 90s. And they're all roughly compatible with each other. There's an RFC that standardizes the Open PGP protocol. So this one, we're just going to generate a key, and we're just going to call it Alice's key, and we're going to associate Alice's email address with it. The passphrase will encrypt the key with a block cipher, so that passphrase is going to get used to encrypt the private key itself, and you'll need that passphrase again when you go to decrypt anything. And then just tell it we're going to use RSA as the algorithm. Once we have a key, we need to output it. So we're going to say this will include the private keys with the secret flag here, and output to this file. And then all the public keys will just go in this file. Then when we want to use them again later, we just say import keys, and here's a whole list of them. So encryption's pretty straightforward, just the plain text file you want to use and the output file name. Armor here doesn't actually provide any more security. It just encodes the message into a base 64, just kind of its own standard OpenPGP way of doing base 64. So that's very handy if you're going to email something or otherwise put it over something that doesn't handle raw binary data very well. And we'll say that we're going to sign the message as well as encrypt it, and then the passphrase we used before for the private key, since we have to sign the message with the private key. And then we want to encrypt it for this recipient here. And then decryption, also pretty straightforward. Just take the ciphertext file, our output plaintext file, and the passphrase for that private key. Assigning a message, if you want to do just signatures without encryption, you just call the sign function here. And again, plaintext output, armor, all pretty much what you'd expect from the encryption example. And again, for verify, all very straightforward. And now there's music. Okay. We'll just hold a minute for the music to go away.
Your presentation is on hold. Please check back.
Any questions so far?
No
Nope,
change.
it's still here.
Which of these encryption methods are used by our credit cards?
That depends on the bank, I think. I couldn't tell you offhand.
If you're talking about your web-based transactions, what does SSL mean?
Usually RSA.
Still going.
What?
Is it?
No?
Nope,
Oh.
it's stopped.
I'm just hearing it on
It's
the
just there.
Okay. So, the one big problem with RSA is you've got these public and private keys. Anybody can just shove a public key out there. How do you know that key actually belongs to Bob or Alice or whoever else you want to communicate with? So how did Alice get this key in the first place? Did she get it over email? How does she know that email actually came from Bob? Did she have Bob's phone number already and she just called him up and said, hey, is this actually your key? And how did she get that phone number already? How paranoid are you about your links of trust? Get it from Bob in person, then you can be pretty sure of it. Maybe you got it from somebody who knows Bob. Do you trust everybody in that chain? Or did you get it from some trusted third party who's supposedly impartial? And there's been a couple different ways to solve this problem. The PGP way was this web of trust, that you know somebody who knows somebody. And there was a way to set the level of trust on a given key that, yes, I met this person right face to face, and I know this is their key. But maybe if you know somebody who knows somebody who knows somebody, maybe you want to reduce the level of trust you have in that key. And this was all worked out in the OpenPGP standard. But the real problem here is, how do you get people together to sign each other's key? It's kind of just us nerds doing it. There's been parties for just doing this, but nobody outside of us nerds really does it ever. So nobody was really happy with that solution, so SSL had the idea of the trusted third party that's supposedly impartial. And they called that third party the certificate authority. The problem we found with this was that CAs do dumb things sometimes. VeriSign, a couple of guys once came up to them and said, "We're from Microsoft, give us a couple of Microsoft code signing keys," and VeriSign just gave it to them. And found out about a year later that they weren't actually from Microsoft.
A year later.
Yeah. So that was back in 2001, I think. So VeriSign had a monopoly back then. That was also a big problem. Yes, I think we all have very fond memories of VeriSign back in those days. So that's less of a problem now that browsers have kind of taken keys from other certificate authorities. But still, this works. Maybe hasn't been entirely successful. The last way that is sometimes kind of overlooked as being a way because it just kind of happened by accident. I think a lot of us use SSH day to day, and no doubt when we've connected to a new server, we see this big message here. Has anybody actually called up the sysadmin and said, "Hey, is this fingerprint actually right?"
I am the sysadmin of a lot of those, and I don't know if the fingerprint is right.
Exactly. And without bragging too much, I think there's probably some important enough people in this that have access to data that shouldn't be public. And we just kind of trust this, that the first time we connect, it's probably right. And the world's not falling apart. This seems to work. I'm not going to say this is right. Your dentist will yell at you for not flossing. Your cryptographer will yell at you for not checking your key fingerprints. I'm not going to say this is right, but I can't exactly say it's wrong. The world's not blowing up because of this. So do with that information as you will. Moving along though. So hashes or digests, terms are basically interchangeable. The idea behind this is we're going to take a whole bunch of data and we're going to shorten it to a specific string. And digests have a lot of different uses. The hash that Perl uses in data structures is meant to take a string and then map that to a memory location. That's not a cryptographic hash. It would be way too slow if it did it that way. But that's one type of hash. There's other hashes that protect against accidental damage. Any TCP packet has one. Many other different protocols have one. And it's usually a fairly quick one, and again, not cryptographic. But it'll protect fairly well against accidental damage. The ones we're really interested in tonight are going to be the ones against deliberate damage. And the ones we want there, if there's a single bit of change anywhere, we want this avalanche effect, where that single bit is going to make a drastically different output when we finally get around to it. We also want to make sure it's hard to figure out whatever the original data was if you had the hash. So I can hand you a hash and tell you, figure out what this originally came out to, and that would be very difficult for you to figure out. We also want it to be difficult to find collisions, where there's two different pieces of data that will hash to the same value. And this is complicated by something called the birthday problem. Now let's say you had a party and you wanted to have a 50% chance that someone in the room is going to have the same birthday as you. And to do that, you'd need to invite 253 people. But if you change the problem a little bit, you say there should be a 50% chance that any two people in the room should share a birthday. Then you only need 23 people. Just that little bit of change makes a drastically different effect on the number. And where this comes into play with digests is we're not looking necessarily for a collision between a specific piece of data and something else out there. We're looking for any two pieces of data that might collide with each other. And what this effectively means is that compared to a block cipher, where we went through all that math and said that 256-bit cipher was as good as we're ever going to need in all likelihood, Here we're going to have to double that to take into account this birthday problem. So a 512-bit hash is, again, probably as good as we'll need.
Okay.
There's also a lot of dead and dying hashes. MD4 was kind of the first major cryptographic one to come out, but it was completely garbage. MD5 was an improvement on it, and it held on a little bit longer. SHA1 was, again, another improvement, and we thought this was going to be so good. And then in 2005, somebody figured out, nope, it's not good after all. SHA2 had already been out at that point as a further improvement. And all of these have roughly the same kind of internal mathematics. And for that reason, when SHA1 fell, people started getting nervous about SHA2. It's not quite as similar to the previous ones as MD5 and MD4 are to each other, but it was still enough to make us nervous about it. So once again, NIST started a new contest after the break in SHA1 and just wanted to find something that was completely different from what we had before. In 2012, they picked the winner of Ketch-Ak, which I'm told is the correct pronunciation. And Ketch-Ak can go all the way from 224 bits to 512 bits. In the intervening time, nobody really improved the attacks against SHA2. And so maybe that wasn't so bad after all. But we've got these other things now. Nice to have options. So there you go. On CPAN, you'll find all the cryptographic hashes in the digest namespace. Not everything there is for cryptographic use. Adler32 and CRC there are just much shorter hashes that are used for checking, like protocols for checking to make sure the bits are okay inside there. But they're not for cryptographic use. The ones you want to be looking at is, well, Digest SHA3 is there, and unlike CryptRandall, they've actually renamed Ketch-Ak to SHA3, so there won't be any confusion about that. And then all the other SHA3 finalists down here, they're all in there. And of course the older ones as well. If you're using MD5 or SHA1, you want to be looking at making some changes to that application. SHA2, you probably don't have to panic at this point, but SHA3 is probably what you want to use for new stuff. But nobody would blame you for using SHA2 either, to be honest. And they all have pretty much the same interface where they export a function. And it's always going to be in this format of the digest name, the bit size, and then some encodings. This could be taken off if you just wanted the raw bits, or it could be base 64 or hex here. And then you just feed it a string, and it outputs that big long hexadecimal string. So all pretty straightforward. So password storage is something we all kind of have to work with, and there's been many generations of bad attempts at this. Old Unix system, when they finally got passwords at all, started out with plain text. That's not really good, and so people went to this crypt function, and eventually that was found to not be very good either. And then after that they went to MD5, and there's been many other things since that we'll get into. So, do not use the crypt function. This is also part of the standard C library. And again, it's straight up available in Perl. And in its default mode, it's based on DES. And as we covered with block ciphers, DES isn't good enough. You can brute force it pretty easily. And what's more is that however long the password is that you stick into crypt, it's going to truncate it to 8 characters. And it's going to treat them as 7-bit ASCII. So if you put in a UTF-8 long character, it's just going to ignore that. Now, 8 characters times 7 bits is 56 bits, which is exactly the DES key size. And in truth, it's not even 56 bits. You wouldn't have to brute force that. Have you ever used a password that had, oh, let's say a carriage return in it, or a device control 1? I bet you'd never use a password that has this whole side of the ASCII table.
Maybe the bell.
Maybe the bell. I bet a lot of applications would break if you tried. So that gets rid of 1/4 of the possible characters right there. You only have to brute force based on this. So that's actually a lot less than 56-bit security to begin with. And we know 56 bits isn't enough. So don't use crypt. We started going along the right path with hashes. If you take a password, hash it, it's always going to be the same length, and even the person who owns the database won't be able to figure out what the original password was, because that's one of the properties of a cryptographic hash. As long as we choose a good hash, this seems to be okay. Except for rainbow tables. Rainbow tables, you've pre-computed the hash of a whole bunch of different passwords. So in this little one-liner here, we're using the MD5 digest here. And we're going to start with and we'll just run this 5 times. You'd run it a lot more, of course, to get all the passwords. And we'll just hash that password, and we'll use the magic of the ++ operator here to iterate through the string. And so here we just have the password and then whatever it hashes into. So all an attacker would have to do when they get to your database, and it's a big embarrassment for your company, they just have to match up the encrypted or the hashed value over here to the original password. And then they can break your whole database that way. So the solution to the rainbow table is the salt. And we just add this little random value to the password and then hash it. And now the rainbow table would have had to have the same salt. And if we use a different salt on every single password, and our salt comes out of a secure random number generator, they're only going to get one password at most, not the whole database. And they're going to spend a lot of work to just get that one password. So it should be different for each password. It should come out of a different cryptographic random number generator. And then you're good against rainbow tables. So then there's this other little trick, the timing attack. So Mallory's just sitting at home, and he sends to your website a possible password. Now, if you think about the way matching strings will work on most programming languages, including Perl, it's going to go through each character in each string individually, and then as soon as it sees one that doesn't match, it's going to fail out. So, if it takes a little bit longer for it to fail out that way, then Mallory knows he got some part of the password right at the start. And you might think that that nanosecond of difference wouldn't be measurable over the internet, but it turns out if you just try it 100 times and just kind of average out the differences, you can actually do this practically. It was actually done against OpenID and OAuth right over the internet.
Wild.
Salted hashes do make this a little more difficult, but not impossible.
Limiting number of tries would be the obvious defense.
Yes,
But not
if
that,
you're
it wouldn't help
willing-
that much.
if you're willing to spend a week or a month on it, if you send 10 tries per second, it pretty much works out.
Still,
So
you can,
it's-
if you're really into it, you're going to be sending tries from different
Yeah.
locations. You know,
Yeah.
You're going to have a bunch of PCs out on the network, and all of them sending the password.
Mhm.
So it depends upon what you're after.
Yeah. There's a little trick though we can do to make us completely secure against this. And we're going to match a string so that no matter where in it, we're not going to have that fail fast property, basically. So here we do check that the length is the same between the two strings and will fail out if they're not the same. Note that if you're using a hash, those are going to be the same length anyway all the time. So then we split each of the strings into their component characters. And then we're going to do an XOR operation. And one of the properties of the XOR operation is if you XOR something with exactly the same bits, it's going to come out to 0. And again, you can look up through the truth table if you don't believe me, but trust me for now, that's what happens. And so if this does match, ends up being 0 all the way to the end, that means they did match. And so we just iterate through the strings, keep ORing it back to this does match, and if we're 0 down here, we can return true, that yes, the strings did in fact match.
So you just force it to look at every character.
Right.
Whether it matches or not.
So, salted hashes up until a couple of years ago were just fine, as long as you use a good hashing algorithm. Around that time, GPUs have been becoming more general purpose computation devices, and it was found that you could break a hash password relatively easily if you had a good GPU. And the mistake we found that we made was that cryptographic hashes are meant to be fast. Not so fast that they negate their own security parameters, but we want them to be as fast as possible, really. We don't want them to be fast for this. If it takes an extra second for your user to log in, they're just going to be putting one password in. Oh, it worked, that's fine. And if it didn't work, they just try again a few more times, maybe. And if it takes an extra second for that to come back, that's okay. If that extra second was spent doing a lot of work on the CPU, the attacker is going to have to do that same amount of work when they try to brute force through your password database. So the solution was bcrypt. This actually came out in the late 90s. Nobody really paid much attention to it then, but then when these GPU attacks came out, people started looking back at it. And bcrypt is slow on purpose. And there's in fact a little cost attribute on it that you can tweak that up every year as Moore's law goes up and make it a little bit more difficult to hash the password. Another alternative is scrypt, and this has the property that it's supposed to use a lot of memory. And GPUs are very bad at shuttling things in and out of memory. They're good for just raw computational power. As soon as you hit the memory, they slow way down. And scrypt is kind of designed to do that. It is somewhat newer and not as well studied as bcrypt. If you chose bcrypt right now, you'd be just fine. If you chose scrypt just right now, you'd probably also be fine. But neither one of them is bad at this point. Scrypt may well be where we end up heading. So, to bring this all together, we noticed over just the past 10 years even, the state of the art has changed a lot for how you're supposed to be doing this. And people will call you an idiot if you don't do it right. And what that means is your application should be designed to accept changes in your algorithm easily. So if the way you're using it now is completely broken this morning, by this afternoon, you should be able to push a change to production that fixes it. And the best solution I've found so far for this on CPAN is often passphrase. I have a few caveats on it. It doesn't match the strings in a way that handles tiny attacks. And it also doesn't really have a plugin architecture, which means the often passphrase distribution installs everything. And you're going to get all sorts of algorithms and other CPAN modules that you don't necessarily need. So it's kind of a big dependency maze. But I think this still is the best solution out there right now. So in this example, we're just going to have this, what class we're going to use. In this case, blowfish crypt, which is bcrypt. And the parameters will pass in also. These would generally come out of a configuration file somewhere. That makes it much easier to change than having them right in your code. It will generate a salt for us out of a good random number generator. And this bcrypt cost is also something else you want to put in a configuration file. And then down here, the interface, again, is pretty straightforward. We just call the constructor with those parameters and whatever passphrase it was the user gave to us. Down here we have this as RFC 2307. And this is what allows us to change things up very easily. Within that string, that RFC defines a way to encode everything together into one string. So that will include the salt, the cost parameters, any other weird parameters that whatever thing comes out in the future will have, and the encrypted password in there as well. And then the app would configure whatever those parameters should be, and then when the user logs on, since we can't break our own database by design, we have to wait for the user to next log on, and if it doesn't match these parameters that we configured before, we're going to rehash the plain text password that we now have, and then put that back into our database using the new way. So a user that doesn't log in very often is still going to have a old insecure password, but there's honestly nothing we can do about it. So when we go to check this, we don't explicitly say the blowfish crypt class name. We just call auth and passphrase with from RFC 2307, and then whatever passphrase we got out of the database. And then this auth object here will be whatever subclass it needs to be based on that string. Now down here, we want to match that whatever we configured as being our preferred method, we match exactly. We don't want to match a subclass of that, we want to match exactly. So we use ref here, not is a. So then we also check whatever authentication parameters we had also configured. And we want to check for the bcrypt cost parameters. We kind of left that part out because that can get a little bit hairy to not assume bcrypt parameters. You're going to have subclasses that can check each individual type. That gets a little more hairy for one slide than I wanted to go through here. But that's the way you'd want to go. So then we have this new database passphrase that after we've indeed matched the user's passphrase that they gave us, we just rehash it and save that back in, and now our user is on the new method of encrypting passwords.
So I guess I don't get why you would need to do some other test besides just recreate it with your default parameters. I don't understand the bottom thing checking for bcrypt cost, but
So a different cost parameter will give you a different output. So,
right. But if you do the thing with the passphrase class and give it the new parameters, why would you need to check other stuff?
well,
Is it like the parameters changed but the class didn't? Is that sort of it? Okay.
yeah, the cost can.
So you maybe want to just check all the parameters instead of just the class.
Right.
Okay.
And then do that in a way that doesn't assume
Assume
blowfish.
anything, right.
Yeah.
Well, just checking the parameters would be the hard part, I guess.
So, what I hope you took away from all this, use a cryptographic random number generator. OTPs are useless in practice. People will go on about them, use that information to win arguments on the internet, and otherwise forget about it. And then hopefully how to use block ciphers, public key crypto, and hashes in practice, and also where we're headed with storing passwords, which is kind of the big thing where we all get affected by this, other than maybe SSL. So, any questions?
Is your slideshow going online?
Yeah, I'll put it up.
But much of the content has been at Wumpuskin.
Yeah, that's.
Yeah,
this is
that's
very
been
much
nice.
the condensed version of all the blog posts I've been doing.
I haven't looked at them all. I should go back and look more. Because I was reading them for a while, but I fell behind.
Very nice. Very nice, thank you.
Yeah.
Clarified some things.
My handy.
Yeah, I feel like I've been watching your presentation for most of the month, which has been awesome.
So the often passphrase, it's a one-way hashing? also?
Yes.
Or hashing
It's
is one-way.
Decrypt Blowfish is a block cipher itself, but it's kind of used in like it's a hash.
I knew things had been changing, but I didn't realize how much they've been changing
Yeah.
recently.
It's hard.
Yeah.
So I don't use often passphrase. I wrote my own thing. And so it looks like often passphrase is actually somehow storing the type in the password
Yep.
field with the hash. So is it just delimiting it somehow?
Yeah, that's the RFC
Okay.
specifies how to do that.
All right. I was wondering because I just store it as a separate field for mine.
Right.
But
Most people do.
Okay.
Once I saw this, like, this is what we need to use. Yes.
Yeah, I hadn't heard of that one before, so.
Neither had I before I started on this presentation, actually.
But
Yeah.
that
And
to
then-
me sounds a little scary because if somebody gets that whole, well, if you're storing it,
Well, they're getting your database anyway.
if you're storing, you know, I know from your talk a couple of months ago, you had the actual encrypted data in one location or in one server, and your keys and configurations are different. So you actually
Sure.
have to break
Two.
two different places to get to that information.
But using often passphrase doesn't necessarily affect that.
No, because
Yeah,
you
you
could
still
still
wanna
have,
put
you
on
could still have you're passing in your key and all that stuff in through those configuration parameters that he
Right.
listed. Where you got that from, who knows? Now, in my case, I'm doing the encryption over here and storing it over here. which
Right,
is
but
different.
I think the RFC was, if the RFC is going to store some delimited method or use some delimited method to store what it used to encrypt, then isn't that sort of giving an attacker a hint? And
Honestly, they'd have those parameters in the database anyways, because you need to store the salt and the type within the database. And if you do that as one big string rather than different fields in the database, I don't know.
If you don't have that, you won't be able to verify your user's password.
Yeah.
You have to have that info anyway.
right, yep. But I mean, you'd store it somewhere other, someplace other than where the hashes were stored. So.
I don't think that would cause a problem because when the person steals the database in order to get the passwords, their whole purpose is to figure out what the reverse of that text is. So even with that, I don't think it actually helps them that much to find out what the actual text is because they want to find out what to put into the front end to get access. And I don't think all that stuff helps that much. Because they still have to brute force a whole bunch of stuff in order to find it.
One way to think about security is an attacker can know everything about you. They know the IP address of your server, they know what kind of database you're using, they know the versions of your web server software. They know everything about you except one little encryption key. And if they don't have that information, they can't do anything. And you compare that to a situation where, I have to hide what algorithm I'm using because it's not a very good algorithm and they'll break it if they know what it is. That's not very good security. It's just this one little piece that stops them. Now, there's no reason to tell them what database software you're using or any of that. But if they do know that, and they can probably figure it out, you should be okay. So just knowing what algorithm you're using.
Just don't tell them what version of Internet Explorer you're using.
Yeah.
a reasonable number of attackers are going to be inside your organization anyway.
Yeah.
So,
Well, maybe your organization.
organization. Most organizations. A reasonable number of attackers are in the organization.
I vetted Dave. He's okay.
I never attacked JT.
Okay, so if it's just you and Dave, you're pretty safe.
It's Colin I'm worried about.
Yeah, I'm worried about Colin too.
Well, hopefully
Them
Colin
West
doesn't
Coasters.
watch this video.
Yeah.
Some of us have students traipsing around all day long.
Students.
I have students in my office too. They don't know what's going on.
So you think.
Most of them, that's probably true.
You think they're probably hacked into your server?
Are you kidding? They're just glad Dad's not yelling at them.
His students are genetically tied to homeschooled like that.
All right. So next month then, Dorothy's going to talk about Jenkins. So that should be interesting. Does everybody here know what Jenkins is?
Not off the top of my head.
really.
I think Hudson, the continuous automation,
Okay.
deployment automation, testing.
It's a thing I want to do a lot more of.
Hey, you never have time to do that, do you?
I do. Well, see, here's the thing. I've actually built a few tools to do some of what Jenkins would do for me, but I would rather start using something that, like Jenkins, that can do a lot more for me that I don't have to write. Because otherwise, I'm maintaining two things.
I think Jenkins is written in Java though. That may be blessed.
Is there a bridge for Perl Mongers?
Jenkins is an app.
I know.
Jenkins is an
That will help
Is it
Perl
a framework?
programmers program more Perl.
and it likes to use Perl scripts. And it will automate Perl applications, and it uses Perl plugins.
Oh. Report?
And uses plugins in lots of different languages.